Hey everyone, and welcome to day 7, the last day of techniques for differentiation. We're going to start kind of back at the beginning and then work our way forward from this unit. Tangent line approximation. So if we zoomed in extremely close to any function that you have, it would look like a straight line. And even though that's not the case, because we're zoomed in so close it would look like it, we can't see anything different. That's kind of just exactly like what we're doing with the tangent line when we take the derivative. So straight line that we think when we zoom in is f of x at x equals a and has the slope that's equal to the derivative. So all this is saying here is that it's y equals y1. We are used to seeing it as y minus y1. And so we would used to see it as y minus y1. We just added it over, plus the derivative, or the slope. The derivative is the slope, at x minus x1. So if we think of that right as the tangent line approximation, well, that's all it's saying is that if we have f of x, we need to find f of 0 to get us a point. Sine of 0 is 0. So we have the point 0, 0. And then we have to find f prime of x. Well, we know that's cosine x. If we find f prime of 0, it's cosine of 0, and that equals 1. So you're given y equals 0, that's our y1, plus 1, parentheses, x minus 0, and you're just given y equals x. And let's see that on, and so I'm on Desmos.com, so right here is y equals sine x. If I zoom in really close, notice how close that is. Look what that looks like. It's just a straight line at y equals, it's a straight line with a slope of 1 going through the origin, which is just y equals x. So again, zooming out, it doesn't look curved anymore, but zooming way in, it looks like the line y equals x. And that's exactly what we were looking at when I did that example in the notes. So why don't you guys try to solve this? So actually, let's just do it. F of 0 equals e k to the 0, well, we know that's just 1, because anything e to the 0 is just 1. And if I find f prime of x, which equals e to the kx times k, if I find f prime of 0, I'm just going to get k. Why? Because e to the 0 is just 1, so I'm just going to get k. So if I'm going to find the local linearization, y equals, well, I have my point 1, the slope plus my slope is k, parentheses, x minus my x value 0, so I'm going to get kx plus 1. And if you were to graph this, which we're not going to do right now, but if you could graph it any value of k, you would get this line when you zoomed in really close, as we did to Desmos. So in this case, the local linear approximation of the function f at x equals 2 is approximate. This is the function. It's asking what is the value of f of 2 plus f prime of 2. Very straightforward. Find f of 2. 2 e to the 4th times 2 minus 3 e to the 4th plus 5. We know that's 4 e to the 4th minus 3 e to the 4th plus 5. F prime of x that we need to get is 2 e to the 4th minus 0 plus 0. So we're just going to get 2 e to the 4th. When I add those together, f of 2 plus f prime of 2, we're going to get that to be 6 e to the 4th. Oh, minus e to the 4th. Let's go back there. Four e to the 4th minus 3 e to the 4th is just e to the 4th plus 5. So if I add those, I'm just going to get 3 e to the 4th plus 5. That was a local linear linearization. Now we're going to get into something completely different called L'Hopital's rule. So we know what we've said in the past. If I was to calculate this and we plugged in 0, you get 0 over 0, and that's indeterminate form. Indeterminate form right there. And we know that when it's indeterminate form, there's something that we have to do otherwise than plug in. Usually factor, conjugate, complex fraction, whatever that is. Well, in this case, when we look at this, there's nothing that we're going to really multiply by. And so we're kind of at a standstill. So what we're going to do is look at it in terms of local linearity, or the local linearization that we just did. So suppose we let the numerator equal 2x equal f of x and the denominator to equal g of x. Then, since we're looking at as a limit as x approaches 0, we can say that we can find the derivative to give us the slope at that specific value, which we say is 2. And if we zoom in on the graph to the origin of the numerator and denominator, then the tangent line that we're likely to see is going to be 2x. The reason being, we did y minus 0 equals 2, parentheses x minus 0, you get y equals 2x. So this is the equation of the numerator. We also get y equals x is the equation of the denominator. Slope of 1, the derivative of x is 1. So using local linearity, we're interested in the ratio of the numerator and denominator, the ratio of how close they're changing at, change in y over change in x. And so in this case, the limit as x approaches 0 of that, we can state is approximately 2x over x. And therefore is just 2 over 1. Well, where did we see 2 over 1 before? F prime of 0 and g prime of 0. And so what this is trying to conclude here is that as x approaches 0, the approximation is equal to 2. The limit is equal to 2. And we did that based on the fact of the derivatives. We know that as we get really close, we're looking for the rate at which it's changing as gets close to as we approach 0. And so we're looking really at the slopes of the lines, and we looked at the rate of the change, which equaled 2 over 1, 2x over x, which then simplified to 2 over 1. The key here is that it's equal to the derivatives. The derivative of the numerator divided by the derivative of the denominator. So here's a picture to help you. It's in your notes. You can look. So one of the rules for L'Hopital says that the limit of the quotient of the functions is equal to the limit of the quotient of their derivatives, which is what we just talked about, provided that the given conditions are satisfied. It is especially important to verify the conditions regarding f and g, and we'll get to that. It's also available for one-sided limits and for limits that go to infinity and negative infinity. And for special cases in which it's f of a equals f of b, which equals 0, and that the derivatives are continuous and the derivatives are not equal to 0, we can see why it's true, and using the definition of limits, you can see why here. L'Hopital's is kind of going backwards from what we are used to. We're used to using limits to give us derivatives. My example here is that we know f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. What we're doing here instead is using derivatives to give us limits, kind of using what we know, to go backwards a little bit. So here's the rule for L'Hopital's, which makes finding limits that are difficult much more useful. If f and g are differentiable and the numerator and denominator equal 0 at the point that we're evaluating, and the derivatives don't equal 0, then we can say the limit as x approaches a of the function equals the derivatives evaluated at the limit of the numerator and denominator. And so since we can use the idea that the limit as x approaches a is equal to f prime of a over g prime of a, when we get to one like this, you have to show what g of 0 and f of 0 is. Well, even before we can show that, we have to say what f of x is, e to the t minus 1 minus t, and g of x, or g of t, it should be t's, equal t squared. So those right there, we can show that's 0 divided by 0, and therefore, since it's 0 divided by 0, we can use L'Hopital's rule. How do we do that? Limit as t approaches 0 of e to the t minus 1 minus t over t squared. We can say that that is equal to, using L'Hopital's, as t approaches 0, we are going to take the derivative. Saying L'Hopital's here means that we're taking the derivative. what we see here is that this goes to 0 and this goes to 0 still. And so therefore, we have to use L'Hopital's again, which can be done. That's what I want to show you on the first example of e to the t over 2. Well, that's equal to e to the 0 over 2, which is equal to 1/2. So that's how we're going to have to do it. When you have 0 over 0, infinity over infinity, negative infinity over negative infinity, you must, and there's no other way to do it, you can use L'Hopital's. Even if there is another way to do it, you can still use L'Hopital's. Use L'Hopital's by putting an equals and an LH, still writing the limit sign, but taking the derivative of each of them. So looking at this one, we can see that we're looking at end behavior here. And if we look at e to the negative x, we know it's the exponential reflected over the y-axis. So instead, we're going to, oh, that's off. Let's look at that again. So we know that this is going to 0. And so with the last bit of this 5x and 7x, we know it should be just 5 over 7 due to the fact of looking at end behavior and multiplying or dividing by the highest exponent. Same exponents, so therefore same denominators. But moving on, if we didn't know that, we would get infinity over infinity. And so let's just look at what that would look like using L'Hopital's rule. We're going to use LH, so we're going to get 5 minus e to the negative x over the limit as x approaches infinity over 7. And we know that goes to 0 using that information up there, and you're going to get 5 over 7. So with this one, notice that if you say f of x, or f of 1, excuse me, noticing that f of x is x to the 6 minus 1, I'm not writing that down due to time, is 0, and g of 1 is 0, so therefore we've proven that 0 divided by 0. So what I'm going to write down is limit as x approaches 1 of x to the 6 minus 1 over x to the 4th minus 1 equals LH, L'Hopital's, the limit as x approaches 1. Now take the derivative, 6x to the 5th over 4x cubed. And now what I can do is just plug in 1. 6 times 1 to the 5th, if you want to write that. 4 times 1 to the 3rd. I'm just going to get 6 over 4, which is 3 over 2. So notice with this one, I had to prove it was 0 over 0. In regular, I would write it all out. Limit as x approaches 1 of that. L'Hopital it. Take the derivative of both of them, plug in 1, and therefore you're good to go. Let's look here. Well, I can rewrite that as the limit as x approaches infinity of x over e to the x. The limit as x approaches infinity of x equals infinity. The limit as x approaches infinity of e to the x equals infinity. So therefore we know we're going to infinity over infinity. And so what I'm going to do is equals LH of 1 over e to the x. The derivative of x is 1, derivative of e to the x is e to the x. And now, oops, need the limit as x approaches infinity. And now I'm going to get 1 over infinity. And so I already wrote out, to save time, so I noticed that the limits as for the numerator and denominator both go to infinity, so I can write equals LH. The limit as x goes to infinity of 1 over x over 1. And again, same thing over here, the limit as x goes to infinity of 1 over x equals 0. And that's our answer. What I would like you guys to do is at least try this one and this one and pause it, maybe that one if you have time. We'll go over this one in class and that one in class. So let's just go with the first two. And so I would like you guys to look at these, see if you have any questions, pause it. I did it all out. If you're ambitious, try this one, but we'll go over the rest of them in class. So pause it please and see what you guys did. For the joke of the day, I know I've been letting you guys down not having it. Why shouldn't you let advanced math intimidate you? It's really as easy as pie. Anyways, have a good day, guys.